Now we're going to change topic. We're going to look at states of matter. Okay, remember all of the stuff we're doing at the moment is fundamentally based on, we're building up our, let's say, talking blocks. The building blocks are the elements. We're now getting our language right. Okay, now states of matter. We all know, and we've all heard the following terms, right? We've all heard solid, liquid, and a gas. Okay? Well, a solid is this. Okay? Essentially, there's a whole load of things that come with solids. Okay? Generally speaking, they're not compressible really. In other words, if you put a pressure on them, you can't squish them. But that's not the case for all. Because, for example, if I've got this is a solid, yes, but it can be compressed. So it depends on what we're talking about, okay? But this would be a solid form, and essentially what I'm compressing is there's air voids inside here, okay? It's not totally solid. It's, if you like, it's a mixture of states. It's a gas and a solid, okay? This foam ball of mine, okay? So if we had a solid, completely rubber ball, it's hardly compressible, very slightly, okay? What about a liquid? Well, first of all, let's have a look. A solid, all the little molecules are all nicely arranged, all nicely together, and they sit right next to each other, and they're nicely packed, tightly packed, right? A liquid. The liquid, as we know, water, molten metal is a liquid, right? Cool drink, fuel, gasoline, petrol. They're all liquids that we've got. Benzene is a liquid. What is characteristic of a liquid is when you pour them into something, they fill up that space evenly. So if it's an odd shape and it looks like this, say, and you pour a liquid in, it fills all the spaces, okay? A solid is generally the shape that it is, all right? So it fills all the voids. What about a gas? All right. Well, a gas basically does the same thing. If we put a gas in over there, we pumped a gas in there, sealed, okay, through a hole, the gas fills all the voids in there as well. Just do it like that, okay? So we've got the three states. Yes, I know. I'm sure that you've all Googled. There are lots of other states of matter as well, okay? Bose-Einstein condensates, plasmas, superfluids, all kinds of different states, right? Fantastic. They exist, right? Plasmas, high energy, high temperature states. Bose-Einstein condensates and things like that. Very low temperatures, right? But yes, they exist. We're only going to be dealing with the three, all right? We're going to be dealing with the three states, and we're going to be dealing with the interactions, because essentially we are going to be looking at, okay, the change of phase, change of state, okay? First of all, okay, let's look at something called Brownian motion. What happens if I take, you can try this, take a thingy of water, and let's say that's water, okay, yep, here's our water there, right, and then let's drop into it a tiny little blob of red ink, all right, take normal water at home and take a tiny little bit of blue ink and drop it in, and watch what happens. It sort of starts swirling down, doesn't it, all right? Like that. And then you start seeing little fuzzy tendrils growing off it, right? You actually see it looks as if it's growing. This eventually, the whole thing turns blue, all right? The whole thing turns, sorry, my apologies, turns red, because it's not blue ink, it's red ink, all right? The whole thing starts to turn red, okay? All right, it turns red. After a while, what has actually happened? Well, what happens inside a liquid, all right? We've got to start looking at, back to one of our atoms now, all right? This thing, if it's in a liquid, it's moving around all the time. If it's in a solid, it's sitting there, but it's still vibrating like this, inside the solid. So is the one, they're all vibrating like that inside the solid. But what is happening in a liquid is this one is able, it's not linked to the one next door. It's able to move around. And it moves around in a random fashion, okay? And eventually, as it's moving along, it hits against the molecules of ink that we've put in. And as it hits it, then what happens is this starts spreading out, right? Now, this movement of this molecule, this atom, or molecule if it's water, okay, moving around like this, it is random. There's no pattern, right? It's random movement. It's in ink, red ink. It's random, okay, there's no pattern. And it's moving, all right? Let me just get it back to my normal boring black ink, okay? It's moving. As it moves, it smacks against the molecules of ink and disperses them throughout the whole liquid, all right? We get dispersion, all right? So these molecules are moving. If they are moving, they've got a specific kind of energy, right? The energy of motion is kinetic energy. It's kinetic is moving. It's kinetic energy. And kinetic energy is equal to a half mv squared, right? The kinetic energy of anything is a half times the mass times the velocity squared. Well, here I've got a thing, it's got mass, and it's moving around, right? So essentially, what we're saying is that this kinetic energy inside here is what is causing this dispersion or diffusion of the others into the liquid. It's this random motion, this Brownian motion is causing diffusion, dispersion. Some of you may have seen, you get little things that look like this. They like a jar. Very often it's like, looks like this, and it's got like a thing like that, like so, and you fill up inside here with an aromatic liquid, and you put sticks inside here. All right. This is a diffuser, all right? What it does is this aromatic oil over here gets drawn up the stick using what's called a wick action, drawn up, and as it's in the air molecules are bouncing around, okay, knocking this aromatic oil scent off and diffusing it throughout the room. Same thing as if you open, for example, if any of you have ever been around when you've opened a bottle of chlorine before you put it into a swimming pool or a bucket. If you're in a closed room or there's no wind blowing, you very soon smell that chlorine from across the room. That's because the chlorine gas has escaped and it has been diffused throughout the room by this Brownian motion. The molecules or atoms of the gas are banging against the chlorine and diffusing it throughout the whole space. So the gas will fill the whole space that it's in. That is why we don't work with chlorine gas when it comes to a swimming pool, for example, all right? Let's just go back to this kinetic energy thing just quickly, because it is quite important to understand. Let's just have a look. The energy, EK, is equal to a half mv squared. Now, the mass, every atom has got mass, right? It's got protons, neutrons, and it's got electrons in it. The electrons are very small mass. We're going to get to that in the next chapter. But essentially, all of those that are inside there have got a mass. So it's moving at a velocity. Now, let's think. If we increase the temperature, what do? We actually, and if you note, if you drop the ink in the previous example into hot water, it diffuses or disperses faster. Why? Well, quite simple. The velocity, remember the mass doesn't change. The mass of an H2O is 2 hydrogens plus 1, H plus 1, O minus 2. There's your H2O, right? So what is happening? This thing, its mass is the mass of all three of these, but it stays the same. The velocity is increasing. So actually temperature is a measure of velocity. And you can see that because if you heat up, as I said, if you heat the water, right, you'll see the ink disperses quickly through it because those molecules of water are moving so much faster that more of them are hitting the ink and dispersing it throughout the liquid all the time. That's what's happening there. So an important thing to remember is, yes, our measurement of temperature is a measurement of velocity of molecules. Okay? So my writing is terrible, isn't it? Okay? Molecules. The faster they're moving, the higher the temperature. If we refrigerate and take all the energy out, right, we slow them down and down and down, and they're getting slower. They get lazier. You know what it's like on a cold day. You want to go to sleep, okay? On a hot day, you want to find a swimming pool or a fan. But on a cold day, you want to crawl under a duvet and have a good snooze. Why? Because basically we're lazy. The same thing happens with a molecule. We remove the energy. We remove this velocity here. And as we remove the velocity, so we reduce the energy goes down. It stops moving. Yes, there is a thing coming called absolute zero. Okay? It's where there's no more energy. Okay? And that is at minus 273 degrees Celsius, which is also called 0 degrees Kelvin. Okay? Right? And what is important about that is that that is where we've reduced the velocity to 0. So fundamentally, this atom or molecule, whatever, just goes to sleep. It just keels over, and that's the end of that. Right? That's the temperature way out there in space. Right, minus 273. That's slightly as a side of the thing, all right? So yes, we've got these processes happening all the time inside our solid, liquid, or gas. The next part of this is to say, right, a phase change, right? A phase change, well, how can we change? Let's have a look. We can go from gas, liquid, and solid. All right. So if we want to go from a gas, all right, let's say we want to go from a solid to a liquid to a gas, which is the normal phase, right? So this would be ice to water to steam. All right. So what we've got is we've got solid, liquid to gas. What is happening is the solid, let me just change the color here. Okay? The solid goes to there. So it goes from there to melting, right? The reverse would be freezing. Liquid to a gas would be boiling. Or evaporation. Downwards would be condensation. Like that. Okay? These are all in the textbooks. Every single textbook I've looked at has got a great drawing of this. Some of the things go this way though. And that is called sublimation. Usually dry ice and iodine. They sublimate. All right? Okay. That's what they do. Now, you're going to see in the thing coming up, they're going to give you various substances and temperatures, and they're going to ask you to identify what phase it's in. Okay? This is what you're going to get. Okay? Now, what we do is we always do it like this. We say, right, let's just draw this diagram here. Okay? Bear with me a sec. Over here, I'm going to put in time along this axis, and over here, I'm going to put in temperature. Okay? So, let's say over here, I put in 0 degrees Celsius. Over here, I put in 100 degrees Celsius. And over here, we're going to put in a line. I'm just going to change it to a blue one for a change. We're going to have a line doing this, 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 and this. This 0 degrees centigrade point, okay, that is given a specific name. Over here, it's solid. Over here, it's liquid. And over here, it's a gas, right? What is this thing? Let me just label it. A to B to C to D to E to F. What's happening here? Okay? Well, it's a solid. 0 degrees Celsius. This has got a very specific name, hasn't it? Let's put it in red. Freezing point. Okay? Also known as melting point. Right? The top one. Boiling point. Okay? All right? Okay. Let's see now what happens. From A to B, all right, it's a solid, all right? What are we doing is the temperature is increasing to 0 degrees. So we are actually warming this up slowly. As we warm it slowly, the ice starts melting. Between B and C, we've got a mixture. We've still got some ice and we've got water. Essentially, they're both at 0. Right, of course you can have that. You've got an ice block with water lying on top of it. The ice is melting. That water is at 0 degrees Celsius. Then at point C, what has happened there is everything has now melted. There's no more solid state. It's all pure liquid from here on. Okay? So from A to B, it's all solid. At B, we start to see drops of water forming on the ice block. And at C, the ice block is totally gone and it's only water at 0. Then the water starts getting warmer. Okay? At point D, the water temperature is now 100 degrees. It starts the boiling. You'll see it in a kettle. If you've got one of those glass kettles or a pot, it starts boiling, it starts bubbling. But there's very little steam. If you let it keep going, you'll see it keeps boiling, but more and more steam come off. Right? So between D and E, you've got a mixture of steam and boiling, bubbling water. Well, what happens at E? At E, all of a sudden, the bubbling water's gone. You better switch the kettle off at this point. Otherwise, it's going to burn out because it's going to be dry. At this point between E and F, you've only got steam left. Right? It's water, but it's a gas water. And between E and F, we've got what we call superheated steam. In other words, we under certain conditions, for example, at power stations, we boil the water, but we allow the pressure to rise, like in a pressure cooker. That is why if you open a pressure cooker lid without cooling it down, that steam that comes out of there isn't at 100 degrees. It's superheated. It could be at 150 degrees, 200 degrees. It's the same as boiling oil, which means it will burn. And it'll burn very badly, okay? Because it's superheated. Someone told me that the pressures and the temperatures can be so high that in fact it almost acts like a knife and it can slice through skin, okay? I would believe that if you got some of that stray gas coming out there because of its pressure and because of its temperature, all right? Now, when you get asked a problem of this kind, they are going to give you, okay, they're going to give you, given a material, okay, what they say is the material is at a certain temperature and they give you its boiling point and they give you its melting point, right? What do? Okay, the quickest way is this. You take the thing and you draw the graph. And let's say they say at minus 180 degrees Celsius is its freezing point or melting point, right? And they tell us at minus 50, okay, is its next point, all right? This is its freezing, this must be its boiling point, all right? And then here it's a solid, liquid, gas. Can you see all I've done is I've used water as the basis. I've drawn the exact same lines here, there, sorry. I've drawn that line and this line. I've put in these 2 points here, okay? Not at 0, but I've called it a boiling and a freezing point. Can you see there? I've put in the lines for boiling point and freezing point, right? Which means that underneath I'm a solid over there. This is what's going to happen, isn't it? So if they say that this is at minus 75, this substance is going to be a liquid at that temperature. It's in there. If it's at minus 190, it's a solid. If it's at plus 20 degrees Celsius, that's up there. It's going to be a gas. All right? So how do we answer that question? Straightforward. We benchmark it to water because we know that freezing or melting point, boiling point is there. Draw the lines in for water and put in the temperature for the material that you're given as its melting or freezing point and its boiling point, and look where you are with regard to the temperature they've asked you, right? So they have said to us, a substance has got a boiling point of minus 50, a freezing point or melting point of minus 180. The temperature is minus 75 degrees Celsius. What phase is it in? We reference it back to this 2 lines here. Okay? Same as with water. So we say solid underneath, liquid there, gas there. And you can answer the questions from that. Very straightforward way of doing it. Okay? And yes, we need to be able to interpret this because, yes, we have it. Liquid oxygen, for example, right? Liquid or dry ice, solid carbon dioxide. Liquid ammonia. Ammonia is normally a gas, NH3, but we get it in liquid form. Chlorine is normally a gas. We get it in liquid form, right? No, we generally don't work with solid chlorine or solid ammonia. It's not necessary to do so, right? There's not a process that we need from an industrial point of view because remember, what we're doing here with the chemistry is we're building up towards how do we make these chemicals to be used, right? Very important part of chemistry is making them up to be used, right? So what we're going to do in the next step is we're now going to start looking at atoms after this, okay? So we've discussed the phases and the states, shown you how to answer them. Have a go at one of them. You'll see them in your workbooks. They're really very easy. Just remember, put in your freezing or melting point, same thing, and your boiling point. Put in the 2 temperatures on the scale. It's the same as water, solid, liquid, gas, and read off where you are. Okay, that's quite straightforward. As I say, the next one we're going to start going, we're going to be going on to actually looking inside the atom itself. That'll be the next session. Thank you for joining me, and I hope that that's thrown a bit of light on that, and I hope that it's staying relevant and staying topical for you, because that's very important as well. Thanks.